Hi, good morning. So today we're going to do a trial attendance check on iClicker. I think usually I will go with a little bit of lecture before we actually do that, so you guys can also take a break at the same time. I'll lead you through. So it's going to be very consistent when we do the attendance check. Don't worry. And for today, the plan will be we definitely want to finish the introduction. It's mainly to clarify at the conceptual level certain terms which we'll definitely try to reinforce over and over throughout the semester, but I think it will be worthwhile to talk them through just for the first class. And then hopefully we will be able to get to the math review about proposition, at least for today. A little bit, if we definitely cannot finish that, but I already posted, I'll show to you. If you go to the lecture site, you can see I already posted lecture 1B. So that will be the slides I'm going to go over. If you really plan to print the slides, maybe don't do that just yet, because I might still do some minor edits before I finish presenting it. So you can expect today, also next week, we're going to spend on lecture 1B, on the math review. We're going to review many stuff which you will need when we get to the case study. All right. This is where we were last time. So we talk about the code of ethics just to let you guys know in perspective. If you really wish to become a professional engineer, you definitely need to be technically competent and knowledgeable in order to do it, right? That's something to keep in mind. And this is basically where we left off over here. We talk about two industrial standards, and I want you to pay a little bit more attention to this one here, DO-170AC. That's for the aviation domain. And later on, I'm going to draw a distinction between mission critical versus safety critical. So the source I cited actually makes reference to DO-170AB or C. I'll talk about it. But let me remind you very quickly where we were last time. So this is a very important diagram, which I'll definitely try to redraw in a different context when we do the case study later. But let me recap. So this is a very foundational approach, very standard for you to verify anything that's of your interest. You got something which can be some working code in Java, C, Python, or simply requirements documents. Some of you might be taking EECS3342 requirements engineering. If you're not, that's okay. So there is another application called requirements documents. Requirements documents. You can think about whenever you try to elicitate some requirements from your customer, the language you put down unavoidably is natural language. It can be very ambiguous. How can you be sure the customer's requirements is, number one, non-contradictory, number two, precise, number three, and complete. So these are the various properties you cannot really reason about directly on the artifacts that's written in natural language. So how do we do it? You have to somehow formulate this document over here accurately into some formal specification. And then the property which you want to verify should also be translated into the same formal language. And then hopefully there will be a tool to help you to prove. And in this course, we'll try to do such check two ways. Manually, just on the paper, pretty much like how you did it in 1090. That's something we'll show you how to do. Number two, we use the local rodent. So it's just a verification tool for you to use. And 4315, for those of you who are in SE, when you take this course next year, the same thing is actually going to follow. But it's just that we're going to use a different approach called model checking. Maybe at the end of this course, maybe when we wrap up, I can mention a little bit about model checking. So that's also something to transition you through. Okay. All right, that's where we were from last time. And just always remember this diagram. It's actually a very nice conceptual view to see what we're doing. Let's move on a little bit. Okay, so these two are the criteria. Make sure requirements are precise and complete. Implementation will conform to the requirement. It will satisfy the property. And let's now try to draw some distinction between mission critical versus safety critical. So I think different people might have different views about how clearly we should really draw the line. I'll try to give you some very reasonable way to really distinguish between them. And then we can maybe come up with some example as we go. I do have some reference over there at the end. You can also click on that and take a look, but let's not go over that. You can see they have a common postfix for this term, critical. What's really critical? Critical simply means the task you're trying to complete it might simply impact something else that's even more important. Basically, you want to make sure the consequence of failing is really something you have to deal with if your system fails. That's why it's critical. But how critical should it be? It could be critical only at the mission level, or it could be critical at the safety level. That's something we'll talk about. Okay, so critical, let's understand. For example, let's say you have a pacemaker that's implanted in the patient's heart. In that case, if it fails, it's going to impact, for sure, their health. And also, they might just simply stop the heartbeat, right? So that's why it's critical. And let's now try to distinguish between safety and also mission. And then I will have to read some passage from the literature together with you, so you get a complete picture. So safety, we actually mentioned about safety last time. It has to do with danger or injury to the human lives or simply loss of human lives. So safety is definitely the number one priority. If you ever have to work for a system that's actually safety critical, you got to be 100% careful. It should be treated as the highest standard. And we're going to see that. All right, for mission. All right. For mission, it's simply an operation that's assigned by somebody else. It's a very general term over here. So you can think about, you might be given a mission to complete your lab assignment. You might be given a mission to maybe develop a small website. You might be given a mission to develop part of the nuclear power plant, right? Anything can be a mission. So that's why mission critical in some way is much more general than safety, right? That's the number one thing you should really get. And before we even do the math review, can you guys somehow relate a system being safety critical and a system being mission critical? Do you think, for example, can I say a system is mission critical if and only if a system is also safety critical, which means they are equivalents? Can I say that? Or should be something else? Let me try to make it a little bit more explicit about what I'm asking from you over here. Let's say we have some safety critical system. We also got mission critical system, the acronym, right? Either we can say a system being safety critical is simply equivalent to, or you can say if and only if. We'll see that kind of symbol when we do the math review, but just for now. Equivalent to mission critical system. Number two, safety critical system implies it is mission critical system at the same time, right? There's another possibility. A mission critical system implies it's also safety critical system at the same time. We got 1, 2, and 3. And of course, they should be logically disjoint. They should be only one. That should be the case, right? Any one of you would like to give a try to tell me which one should be the case? Yes. The third one? Mission critical system. Interesting. Okay, let me just double check, make sure that's really what you meant. You're saying that a system being mission critical should be safety critical at the same time. That's what you meant, right? Okay. Let me give you some example to think about to see if you may want to change your mind. Let's say I'm developing a shopping website for my small business. Or just in more general, maybe in the developing some financial software. It is definitely mission critical because if the system failed, I would lose money, either myself for my small business or my bank. But is it necessarily safety critical? Is there going to be some people who will die from maybe crashing the software? Not really, right? Because you can see safety critical has a very special notion. It has to do with human lives. Okay? So I'm glad you try. So this one here, I just gave you some example. Does not necessarily hold in general. Okay? Obviously, if 3 cannot be the case, then 1 cannot be the case either, right? Because they cannot be equivalents. So number 2 should be the case. All right? Guys, it's more like a little bit warm-up about what we have to talk about throughout the course, right? You have to somehow, you understand what you really learned in 1090 very well, but now you have to somehow use it to formulate what you can observe in the reality and try to analyze it. That's really the takeaway for this course. And this one here will be the answer, okay, number 2. And I want to visualize it for you just quickly, okay? And we know that this one also cannot be true. So if you think about this, if this is the set, conceptually, if this is the set of all mission critical system, only some of them can be safety critical at the same time if they actually involved the human lives. So you will put safety critical as a proper subset, safety critical system, okay? So whenever you have such formal notion over here about one set being a subset or proper subset of the other, you want to always ask yourself, do I know any example that's actually here? Do I know any example that's actually mission critical but not safety critical? So these are the typical 2 witnesses you have to ask yourself. Let's do that. For this one here, you guys gave me very good answer last time. You know, for example, in the automobile industry, self-driving car, and also aviation, you know, developing airplane, or pacemaker, medical domain. They definitely are safety critical, but they definitely are mission critical at the same time, no question about it. On the other hand, this one over here, that's mission critical but not safety critical. One example could be maybe financial software. I think the example we're using here, they're quite explicit and clearly the case, either safety critical or mission critical. However, there might be some cases where you have to know exactly what the consequence might be if the system fell. If it really doesn't involve any human lives, you can always say, you can at most say it's actually mission critical, but not safety critical, right? You got to be careful about the context. But the one we are talking about, they're fine. All right, guys, any questions so far? I hope that's clear. It would be, yeah, I see what you mean. The question was, is it possible to have a system that's actually safety critical but not mission critical? Of course, according to this diagram here, it's not possible, right? But just think about if that really makes sense. If something that's safety critical that involves human life, how can it not be mission critical? Whoever declared developing this safety critical system mission is not mission critical, I think they have some problem, right? Because being safety critical means it can cost human lives. So you got to be mission critical at the same time.
For example, in the mission, they will cost of humans.
Mm-hmm.
So when they consider it as safety critical, so that they cannot finish their mission.
Mm-hmm. No, I think it's not really about completion or not over here. I mean, to finish the mission. It's more about, think of the way to judge is by considering the consequence. By failing the system, if it can cost human lives, then that will be safety critical. That's by definition. If by failing this particular system, if the consequence is only to impact something else, then that will be mission critical, right? So that's why being safety critical, it's not really possible for that to be not mission critical. Yeah, it's good thoughts, but I think I will just give you some standard definition over here and see how we can formulate it as much as possible. Of course, you have to judge. If you really have to, there may be some gray area sometimes that can be some like multiple interpretations. Okay. All right, let's go back and then we'll talk about these already on the slides. And then there will be a relevant standard that we just mentioned about DO178C, that's for the aviation domain. So I want to go over with you guys about this reference. So there's one section there, they define very well about the difference between the two, right? And I also want to draw another notion about criticality level. That's also important. All right, let's take a look. Yeah, I'll make this, hopefully this, I can make it a little bit larger over here. I'll guide you through a little bit, wouldn't really read sentence by sentence, but these passages over here try to really draw the distinction again between safety critical versus mission critical. Okay. First of all, safety means something to do with human life. That's what we just said, right? Also, when you say something that's critical, that means without completing it successfully, you might have some consequence, right? That's critical. And then, so here it talks about what if you failed to actually complete this safety critical system. In that case, of course, it will cost human lives, okay? So this part here, you can please read it. And this one here is really important. This one, let's read it together. Safety critical system demand software that has been developed using a well-defined, mature software development process focused on producing quality software. So that's exactly the purpose for 3342 and also 4315. Because we know the software or the system that we're going to build at least will be mission critical or sometimes safety critical. So we got to make sure the approach or the toolbox we're using should be as professional as possible, right? Okay, so that's really important for you to see. Software development process. You can think about maybe back in 3311, for the software design course, when you learn about design pattern or other software engineering principle, they are also part of the development process that can kind of make it more likely for you to produce quality software. So they are relevant. Okay, so you can think about in 3342 and also 4315. So we show you something called formal method based on math. I will talk about formal method in the next slide. Okay, just understand that. Okay, let's go on. And then let's say some company, let's say they finish building an airplane, let's say, and they would like to get certified so they can start commercializing it. So this will be one possible standard. They have to make sure they convince a third party and the government that you should really give me the license to fly. So this will be the standard we talk about, DO170AB. You might see in the literature, you will see 170AB and 170AC. They are actually the standard. Somehow B was replaced by C in 2012. I actually mentioned that in the slide, but they are the same thing. Okay? And the standard is a set of guidance for the production of software for airplanes, for airborne system. Right? So if you want to really get your airplane certified, you definitely need to consult with the standard. Okay? And this is what I mentioned before, very important keyword here, criticality level. So in this particular standard here, they define different levels of consequence if your system fails. Let's read it together. Okay? Level A is the most severe. That means if you actually fail your system, it's going to be catastrophic. Maybe the nuclear power plant explode, right? And also the next one will be there will be some hazards with some severe consequence. Maybe slightly less severe than catastrophic, right? And the next one will be major and then minor and maybe no effects. So you can think about the kind of assignments we give you to do when you are still receiving the education. They are more like a level E, because even if you fail your assignments, it's not going to impact anybody, right? Except for yourself, of course. But these are the levels you have to definitely understand. Okay? You can think about this one here is the most severe, and this one here will be the least severe. Very straightforward. And then let's see. Oh, this is also important. Safety critical software is typically level A or B. So let me write it down explicitly for you. Level A, level B. When the failing consequence is either catastrophic or hazardous, then that's safety critical, right? Safety critical system. Have you guys heard about the notion, failure is not an option, right? It's actually a famous quote from the NASA flight director. There was even a movie of that, Apollo 13. That's a long time ago. Not too sure if you guys watched that. Anyway, failure is not an option. That's the best buzzword, for categorizing safety critical system. You just cannot fail. You cannot afford. All right, let's now take a quick look at how we can understand. Oh, they just give you more example. Flight or engine controls. If your engine fail, then of course it might cost human lives. Let's now go on quickly to mission critical. So here mission talks about an operation that's simply assigned by somebody else, right? So mission critical sometimes may be safety critical or not. It's not necessarily the case. So that a failure by the operating system, by the system will prevent some operation from being performed. Not necessarily dire consequence. However, if you actually got a mission-critical system to develop, it doesn't really mean the way you develop that shouldn't be professional, right? It doesn't really mean that. And finally, it say that according to the standard, it will be level C or D, at least. Okay, let me write it down over here. Level C and level D over here. If your system has level C, D, or above, then it's going to be mission-critical system. And in some way, you can also see why these two notions are not exactly equivalent, right? Because if you're only able to satisfy level C and level D standard, it doesn't really mean you can satisfy level A and level B, right? All right, guys, I will definitely encourage you to maybe take a look at the passage we went over, so that will really give you a very clear context about what we're doing in these two courses, especially the current one. Any question? We okay? Good. All right, I mentioned about the term formal method. The formal method is also mentioned quite a lot, depending on which industry you go into. But if you go to safety critical industry, for sure, talk about formal method all the time. Formal method is kind of like a method and approach based on mathematically rigorous technique. So you have to use math, specifically the discrete math you learn in 1090. And we'll definitely review what you're supposed to know for this course, for sure. And in the later half of today, we'll show you the roadmap about what we're going to review. And the standard, there's another standard over here. Again, just for your information, that one advocates the use of formal methods. So even the industry, they actually thinks it's really important to use formal method. The pro will be formal methods can, if you develop your system using formal method, it's most likely that it's going to be fit for use, reliable. On the other hand, what's the con? What's the disadvantage? Formal method requires a very steep learning curve. So even if you guys study very hard for 3342 and even 4315, only treat it as more like an introduction to the field. At least you can appreciate what kind of rigor you need to have for you to build such a system with high criticality level. Okay, that will be something to know. And the use of formal methods, we're going to use mathematical analysis, and we want to establish correctness and robustness. That's something you will see in this course, for sure, right? And unambiguously describe. So when you actually use a predicate, for example, there should be no more than one interpretation of what the predicate really means. However, if you describe something, let's say in English, different people might have different interpretations, right? They might just be confused. But for math, unless you really don't understand what the symbol really means, otherwise there should be only a single one interpretation. You'll be precise between engineers and also providing certification evidence. So let's say you actually verify your nuclear power plant or part of it using a formal method. Then the success of the formal verification can be a very strong evidence to show that your system is fit for use. Okay, formal and also. So here's something about healthy and also safety property. Don't worry too much about the healthy constraint just yet. I'll try to give you some example once you have done maybe lab number 1. You can appreciate a little bit more. But here, let's just worry about safety property. Think about the safety property. Let me give you a very simple definition here. That's something you will have to know how to prove and how to specify. Okay, safety property. So whenever we talk about safety property, okay, just make sure. Number 1, every possible states of the system should satisfy it. There should be no time that your system is unsafe, basically. And let me be a little bit more precise. Think about it in this way. Let's say this will be my initial states for the system. And I want to make sure that initial state satisfies the safety property, number one. Okay? And number two, the system, let's say, for example, if the system itself is reactive, in that case, the number of states will just be infinite. You think about a bridge controller. Would you ever expect a bridge controller system to ever stop? Well, of course, unless it has to be under maintenance. Otherwise, it should always be running, right? So reactive system should always be running. Let me write it as a side note. Reactive system is running all the time. All the time. That means infinite number of states. And you have to make sure every possible state of your reactive system is satisfying the safety property, right? I only talk about the initial states. The next one is also important to complete it. Let's say I have a state somewhere in the middle. Let me call this S0. 0, the subscript, stands for the initial. Okay? Let's say I'm somehow in state I over here, arbitrary. Okay? And then I want to make sure every possible way for me to go from Si into Sj, just the next state. I want to somehow establish that, assuming that this is safe. I want to prove that this is safe as well. Let me write it down, and then you might already think in your head, isn't this something I have done already in my math class? Guys, what is that? Induction, mathematical induction, exactly. That's something I'm now still maybe sketching a little bit informally, but I will do that formally, okay? This is something you will have to know how to do. Assuming, so basically assume, Si is safe. You want to prove that Sj, or in some way it's basically Si plus 1, also safe, right? Conceptually, it's not really difficult. Right, that's about safety property. Okay. Oh, how do you actually express the safety property? The property itself is going to be expressed using predicates, which we'll definitely talk about, all right? One more thing to say, one more. And sometimes you might hear people, rather than talking about safety property, there's another acronym people also use a lot called invariant property. If you remember maybe from your previous course, maybe 3101, loop invariance. Loop invariant is a condition that should maintain the same to be true between iterations. Now, invariant property for your system should maintain true between every state, the same idea. Invariant property always should be true, doesn't change, okay? Hey, good for now. I'll definitely revisit this idea again. Let me go back and let's see. All right, let me just talk very quickly about the next two slides. The next two slides are basically trying to distinguish another two notions. Let me show you the title right away. Tell me intuitively how you think. Maybe you just got it. One would be, are we building the product right? That's one thing, okay? Don't worry too much about bullet point just yet. And the next one will be, are we building the right products? Let me write it down, and then let's take a look. Once you get an intuitive idea, I think the slides can be gone over very quickly. Over here. Number one is, are we building the product right? Number two, are we building the right product? One thing I would like you guys to really convince yourself, these are two different questions. They are not asking the same thing. You want to be convinced, number one, they are not the same, okay? Apparently, the right in the first one is used as an adverb, and the right in the second one is used as an adjective, right? So they are different. Without giving you guys more details, can anyone try to guess or try to express. What would be the difference between these two questions? What are we asking? Go ahead. Yes, yes, go ahead.
Are we building the product right? Are we building the product in the right way? Properly, the safety critical
Yes.
rules? And are we building the right product? Are we even doing the right, like, is it the right solution for the operation itself?
Say it again. I would like to hear just one more time. The second one. I like the first one. Basically, the first one, are we building the product right? Did we follow the correct approach to build a product? What about second one? If you don't mind, say it again.
Are we building the right product? So is the product actually going to properly satisfy the solution?
Okay, getting there. Okay, let me start with the first one. Thank you so much. Getting very close. The first one here, are we building the product right? So there is some implicit assumption behind the first question. For the first one here, we are assuming that we kind of know what product we're supposed to build. Implicit. Implicit assumption. We are already given what to build. Or you can think about you're given already some implementation plan, or you're given the requirements documents, or you're given the design. You're just following. Okay? And what can be considered not right when you build a product? For example, you didn't test your software. You only build it, but you didn't really test it at all. Right? That would definitely be considered that it's really not done properly. So here, not right, for example, can be, let's say, without any testing. Since you guys have been this far, I'll get to you. Since you guys have been this far, you know that whenever you build your software or any system, a very important step is to test, right? Otherwise, how can you release it? Okay. Yes, go ahead, please.
Okay. So does the first one only cover processes of building?
It's more like a process, yes.
Or is it also like, if the actual thing, if the thing that you end up building is different from the requirement stuff, is that the first or second?
Okay, I see what you mean. Yes, the first one is about process. It's definitely about the process. The second one is more about, like what you said, whether or not the product we are building is deviated from the actual requirements. That's the second thing.
Okay.
About the goal.
Okay. So the first one is exclusively process.
Yes, about the process. Did you follow the due process or professional process to build a product? So let me make further notes based on your feedback. The first one over here is definitely about the process. And the second one over here would be just about the goal. Are we building the right product? For example, you might say, I have the most exciting sorting algorithm that works completely. But the customer doesn't really require any sorting. They actually want searching. You see what I mean? So it doesn't matter how brilliant your solution might be, you want to make sure you're building the right product for your end user. If you're not really satisfying what they really want, they don't care how efficient or how correct your solution is. So both are important questions, both. Okay? And right products. So this one here, does it deviate from the customer's intended requirements? Okay. But for this course, we are mainly focusing on this one here. You may be given exactly what you're supposed to build, possibly written in English, like a lab instruction or a test instruction, and then you are simply just going to build it, maybe to formulate it in the math. Okay? Okay. And one more thing to say, if you don't mind. This one over here is more about EECS3342, the Refinements engineering course, because in that course, you're supposed to know how you're supposed to get complete and hopefully unambiguous information from your customer. There might be an iterative process you have to follow. Okay? All right, guys, I think without going back to the slides, you can definitely do some reading, but I would like to just go over some diagrams very quickly to conclude these two. Okay? After these two, I think okay, let's go a little bit further, and then we should take a break at some point. Okay, so building the product rights. You can think about this would be the informal requirements. One here, thinking this way. This one here really correspond to, let me just go back quickly, this diagram that we spoke about, right? You can think about something we want to verify. We're going to formulate it against the property that's also formulated, and we check it. That's really the same diagram. Just make sure, okay? So this will be the right way to really build a product, because you translate your informal requirements and, let me see here. Yeah, sorry, the direction is a bit different. You formulate your informal requirements into some system property, and your implementation into some system model. And then you want to check to see whether or not you will satisfy. Sorry, the orientation is a little bit different. It's flipped, but it's the same diagram. And one complication over here, just for your information. When you program in Java, for example, maybe in 1022 or 2030, when you're still building very small application, you don't necessarily have to use like a Java API. You may not use it, or it might just be forbidden by your instructor to use it. You got to build everything from scratch. But in reality, if you're going to build a substantial software project, number one principle will be you don't want to reinvent the wheel if something's already available to you. So this implementation over here depends on library classes. So every mainstream programming language should really support a substantial set of rich libraries for you to use. Maybe you don't really have to implement merge sort or some sorting method yourself. You can simply use it in the library. Another problem is whenever you're using somebody else's work, how can you be sure their work is actually reliable? So that's why the library itself also need to be certified. Okay, that's something I want to mention. You'll also see the more details on the slides. Okay, recap about this, and then we're done with this part. If you want to build a product right, your goal is to make sure your implementation will actually satisfy the requirements. Two things you got to do. Number one, you have to make sure the library that your implementation depends on is itself certified. Number one. Number two, you want to make sure you translate your system and property into some formal notion, and then you will try to do some proof or check. Okay? In 3342, in this course, we'll show you how you can do proofs about this. Of course, for some small system, so you get an idea. That's the first question. Are we building the product right about the process? The next one there is going to be, are we really building the right products? So that one there, basically, by the way, it's the same diagram, but I just want to zoom in to just this part, informal requirements. Okay? So you want to say informal requirements over here, are we building the right products? Does the set of requirements really accurately represent the customer's needs, right? That's really what this is about. All right, good. Any question so far? Yeah. As I said, just today, not so technical, but once we get to later today and also next week, everything will be technical. So it's good to clarify certain things. Yes, Ednan.
This course, are we going to be given like system walls beforehand and system properties, or we have to like?
Oh, good question. Yeah, so Ednan's question was, what kind of property might be given in this course? Okay, I'll give you some example. Okay, let me use this diagram over here. Okay, you may be given, you know what, how about this? I'll make it very precise. I'll create a new page. What could you be expected to do? Oh, sorry, not this one here. Let me do it again. Oh, that should be fine. Okay, this diagram. What can you expect to actually complete for this course? You don't need to worry about library components. You don't need to. Okay, that'll be too much. Okay, you don't need to. Okay, so you might be given. This will be one possible task you will have to do. Number one. So this will be, let's say, given requirements or let's say requirements, something we want to complete, written in a natural language, let's say English, formulates the requirements in predicates. Of course, in order to formulate the predicates in the rodent tool, you will have to know the syntax. So that's something we'll show to you on the labs. You definitely get a chance to practice. That's one kind of task. And the second kind of task will be also for, it's kind of similar. For implementation over here, let me use a different color. Okay? The implementation over here, something like given the natural language description of a strategy of implementation. For example, are we going to do linear search or binary search? Formulates the implementation as, rather than predicates, is going to be so-called abstract state machine. And just for what it's worth, I'll give you just a little bit more information. You will see all of them in Lab 1. And for abstract state machine, it will contain certain constants you may have to use. It will contain certain variables. And also, they will contain certain axioms. Guys, by the way, do you know the difference between an axiom versus a theorem? Are they, can we use them interchangeably, or they're different? Adam, if you remember. We definitely cannot. Yeah, axiom is something you don't need to prove. It's given to you. You can take it for granted. And for theorem, you have to prove it. Okay? Nothing about that. I think it's just about for your context for the system. There are certain constraints you can just assume is actually the case. More like a precondition in some way. Yes? Sorry, say that again. Yeah, proven theorem, we don't really say that. You can think about when you first declare the machine, you actually say these are the things we assume should be true in the first place. Of course, you may also got other theorems to prove. Yeah. They don't really become like a theorem you can use somewhere else. Yeah. Okay, so that's something you guys will also see in the lab. Axioms. Okay, good. And let me see anything. Oh, there's another one that's also important. Okay. That's problem number 2. One more. Over here. And for this part over here, given the formulated property and also given the formulated abstract state machine, we want to prove it, right? So there are 2 kinds of things you may be asked to do. Number 1, of course, prove it, right? You want to, oh, you know what? Let me be a little bit more precise. Number 1, you have to, well, it may not be just a single proof. We'll learn about, in order to prove the correctness of a system, there will be various proof conditions you have to prove as theorems. They are called proof obligations. Obligation means something you have to fulfill or have to discharge in order to claim that your system is actually correct. So the proof obligation, there are 2 things we may ask you to do to do with the proof obligation. Number 1, you just have to prove it, right? And number 2, you have to know how to generate the proof obligation. I might just give you the system description. I give you the property description. Now tell me what will be the set of proof obligations you will have to discharge. And of course, step number 2 could be prove them, right? So these are 2 distinct steps. I think that's more or less what you will be required to do in the course. There might be some small addition too. Yeah. You can see, you can kind of, it will cover many aspects of the this process. So that's really the training we would like you to have. All right, very good. And guys, so what you can do is, you can definitely feel free to take a look at the slides. Everything has been covered, so I don't need to read it off. And, oh, one more thing. We're very close to talk about the notion about refinements, which is the heart of this course. Let me do just one more slide, and then we'll take a short break, okay? And another very important motivation for you. You might be wondering, in 3342 and 4315, why are we not trying to write Java program? And then we actually try to write Java and then try to maybe verify Java directly, okay? So this slide actually addresses that. When you get to the point that you have to write a Java code, you are already quite in the late stage of the development process. Do you guys know what the development process is? What will be the step? Implementation is already quite late. After implementation, of course, you have to deploy. That'll be deployment. What should come before implementation? I do have the answer here. I just want to see if you guys happen to know. So we got implementation, follow that, we got deployment. But what about before implementation? What should we do?
So the first step is obviously the business. So you should discuss the requirements.
Yeah, absolutely. Requirement will be the first one. We can say that.
And then you're gonna have like an architecture of the whole project.
Absolutely.
I might be skipping one or two steps before that, but that's probably before development. So you wanna make sure that you're not starting right.
Yes.
So you structure the whole
Yes.
everything.
Absolutely. Very good. Very good. So, and then actually correctly say that. So you can say roughly there are 4 stages, which I'll show to you on the page. You got requirements to make sure what's the right product to build. And then you got design, in which case you don't really have to program, but you just plan out what should be the architecture. How many classes do you need just to plan? That'll be the design stage. And then implementation, and then deployment. Okay? And then before I don't have that particular, okay, that's fine. So let me show the slide here. So you want to really minimize the development cost. It's very straightforward to ask the following question. Okay, so we got requirements, design, implementation, and release, or deployment. Okay? And so here's the question. So if you were to fix a bug, would it be more costly to fix it in the design phase, or would it be more costly to fix in the implementation phase? Implementation, right? Yeah. The principle should be, if you ever want to fix a bug in your development process, the earlier, the better. What would be the worst scenario you really don't want to run into? After you have release, if you find a bug. Of course, it happens a lot in real life, but you guys are professional. You want to avoid that, right? You don't want to send so many beta to your customer, right? So definitely, and you want to catch the defect as early as possible. And this one just a chart to just to show you about what will be the cost for you to really fix the bug. If you, let's say it's just relative. If you catch the bug in the design phase, let's say if the cost will be 1 unit. If you fix it in the implementation, it's already 5 times of the cost. If you fix it, let's say all the way to release, that'll be 30 times of the cost to fix. You may just go all the way back to where you were in the development process if your customer actually reported the bug to you, right? So that's a very straightforward notion, but it also justifies why in this course and also later 4315, we try to use more like a design language, either Rodin in this course or TLA Plus in the 4315. They are not exactly Java or C like an implementation language. They are more at the design level. So we can describe things at a more abstract level. You try to find any bugs at that level, and they can turn them into code. Okay. And so choice of a design language that should be amendable to formal verification. So guys, the last bullet point is the most important one. So we ought to use a design language that will be amendable to formal verification. So that's why we're using math and also Rodin in this course. So we can use it to prove. And if you're interested, feel free to go to this report. But I already summarized everything you should know. So that's good enough. Right? The earlier you can find a bug, the better. Don't wait until that you have to write a Java code. That's really the key thing. Okay, let's see. Okay, before this is definitely about refinements. How about we take a short break by taking attendance? Okay. So today is only trial just to make sure things work. And you may have to do some resolve your issue just in case you need it. Let me see. Typically, what I will do is I'm going to launch the class, and then 3342, I will start a class. And then on your mobile device, you should be able to see a poll right now showing some picture. Let's say this one here. And you should be able to just click any choice. A, B, C, D, E, doesn't matter. Just click one. Okay, I can see 2 already. That's how you check in. Do you see any option for you? There should be,
It should say that the class started, yeah.
okay. I think for the mobile device, maybe try to use your mobile device for that. I think they'll give you some options, right, to choose A, B, C, D, E.
Okay,
Got it? Good. Yes, good. So guys, it seems like maybe using your laptop may not be the best. It might work, but I think a mobile device might be better. So what I would typically do, I'll do the attendance check for about 1 minute or so. If you got any issue or technical difficulty, come to me right away. I will have a sign-up sheet over here, so you can sign it up, okay, just in case. Question? That's okay. Just click any option. The question itself is not really important. I just want to make sure you're there, okay? Yeah, straightforward, and please use a mobile phone. Today, no punishment if you didn't get it to work. And you can see so far we got 43. That's pretty good, right? Yeah.
Oh, okay. Okay, this is going here.
Yes. Okay, I'll run for 1 minute, and then I'll say, if no more issue here, I'm going to stop it. As soon as I stop, no more argument, all right? And we're done for today, for the attendance check.
Okay.
All right, guys, we're done with this. So I would suggest it's now 12:22. Why don't we take a 3 minutes break until 12:25, and then we'll continue. And we'll make it official next Tuesday when we do it. Mm-hmm.
Put the slide of the natural language.
Natural language?
Yeah.
The slide or the page here?
Yeah, here.
Yeah. Okay.
This slide, I think, yeah, this slide, I think for implementation, you mentioned that you will give us some natural language as description, right? So I'm curious about some system will be different if we use different way to implement them. So I am curious, how can we know the difference
Yeah,
between
so,
different
yeah, of course.
implementations?
Depending on what kind of description I give to you, maybe the description itself is very, how to say, a little bit vague in the sense that you can have multiple different alternatives to implement, in which case either one is okay. Or I can tell you, okay, or I simply say, okay, now use a conditional over here. And now you want to do either this or that. That one's very precise. There should be no ambiguity, in which case there's only one way. It kind of depends. So that's why I say it's a natural language.
Yeah, because you see, if you give us natural language, then it will have many different situations. And then we
But don't
will
worry,
have
the
many
way I write it, it wouldn't be that possible. Yeah, you'll be quite, yeah. I don't, in reality, of course, if somebody tell you, okay, this is how you should do it, if there's a very long strategy description, there might be lots of scope of interpretation. But for our context, it's going to be very short. Yeah. Okay. Hi.
You asked me to give you my note.
Oh, okay. That's for E-class, right? No problem. I'll do it.
Here I'm waiting for the waiting list right now, and I'm also doing the iClicker. And that should be fine, right?
Please do iClicker. No problem.
Okay.
Just follow everything as if you are enrolled. I'm pretty sure you'll be enrolled.
Okay.
Just make sure to do everything that we are supposed to do. Good. Guys, 1 minute, and then we'll continue for 20 more minutes. Yes. Oh, okay. Today you're fine. But starting from Tuesday and anytime, yeah, you got to add a course and make sure as soon as I say, okay, we'll start taking attendance, you want to do it right away. Okay. For today, you're fine. Yeah. But if you want, I don't think there's any class after us. If you really want to try, I can launch the class again and let you see if you can check in. We can do that after class. Yeah. Oh, you want to do that too? Absolutely. Let's do that. Absolutely. All right, guys, 1 moment. Let's get started for 20 more minutes. All right, let's get started again. And then, yeah, I'll definitely let you go in time. Let's just continue. We may not be able to get to the math review, we'll see. But we definitely do the math review thoroughly next week, that's for sure. Okay? I want to show you one more thing that's relevant to formal verification or certification. This one here, this slide here is completely optional. It's only for your knowledge. For those of you who might be interested, actually look into this, I'll leave it to you. Or you can speak to me during the office hour. I'll mention that very briefly. So the formal method that we talk about in this course is for theorem proving. But there's another kind of a very common and popular approach people do to really certify their system in the industry. I'll mention that briefly to you. The idea is very simple. But if you really want to dive deeper to see more case study, you can just Google. There are many papers out there, and take advantage of your library access. You might just be able to find many nice articles. Okay, the key word is about assurance cases. So the idea would be you want to present your arguments of the verification to your customers in a user-friendly manner. What can be user-friendly? If you simply give them your predicate proof, it's not very user-friendly. Only very well-trained mathematician or maybe CS or SE computer scientists can really understand. But in this way, in assurance cases, the way they really do verification, this is the general principle. Okay, I'll show to you. It's more like a top-down. Let's say I want to prove that my system is fit for use. And then I argue that in order to prove that my system is fit for use, okay, let me just give you some example. It could be that it should be fit for use. That's the claim I want to make. And I'm going to argue informally in order to prove that it is fit, I need to satisfy certain things. Number one, it should be robust. Number two, it should be, let's say this. Let me make it a little bit more straightforward. Number one, it should be correct. Number two, it should be efficient. So far, it's very straightforward, right? Yeah. In order to really say my system is fit, it should be correct and efficient, also efficient. And how do you prove? How do I make sure it's correct? Maybe the evidence will be I prove everything in Rodin. And how can I prove that it is efficient? Maybe claim will be I do some asymptotic analysis like what you guys did in 2011, and I show that the system is a big O of maybe log n. I'm making that up. And the evidence will be the corresponding proof. And subclaim number 4 will be I also run my system, maybe on some very big data set for maybe machine learning training, for example. Right? So this will be some testing. And the evidence will be the test report. So you can see somehow we have a tree structure over here to organize different claims together to make the claim. So that's what people also do to actually certify this system. However, you can definitely have different opinions, but some people criticize, which I also believe. The way you organize the tree is very nice, but it's still not exactly logically sound. Who says correct plus efficiency will just be fit? There's got to be some other factor. For example, are you really building the right product? It's not really covered here, right? You see what I mean? So assurance cases is a very nice way to really, for public relation. Maybe I'm a little bit exaggerating, but it's really good to show that you have done a lot. But whether or not the logical connection over here is really sound, like what we're going to talk about in this course, is another story. But people use it a lot. I would say unfortunately. Anyway, so that's something you can definitely look into if you want, but completely optional. Only if you're interested. You can start with this paper here if you're interested. Anyway. Okay, so now we are done with all the context. Let's go a little bit deeper into what we're going to do in this course. It's going to be called model-based system developments. So we're going to build lots of models. You can think about model is more like a formal representation of your system. Rather than writing Java code for your system, we're just going to build some mathematical model, some predicates, maybe some machine. So modeling and formal reasoning, they should be performed before implementing, right? The earlier you can find the bug, the better. So we are more talking about model-based system developments in the design phase or even the requirement phase. And model will be some abstraction. You guys hear about abstraction all the time, maybe throughout your degree. So just for what it's worth, abstraction really is you want to really create something with all the other irrelevant details filtered out. Especially for this course, you will appreciate more. I'm going to show you some diagrams soon. For the same system, we're going to start with some very initial and simple model. We'll gradually try to add more and more information to the model, and we'll try to do verification of each model. And there's a great advantage to that. We'll get there. Okay? But abstraction is about filtering out irrelevant details. That's the principle you want to remember. Okay, so it's a very good analogy here. You can think about the model for you guys as a software engineer. It's like the blueprint for architect, right? So you definitely need a model. So the blueprint doesn't necessarily contain all the details about how to do the construction, but it should be all the critical concept should be encoded in the model or in the blueprint. All right, so this is something you will want to get used to. For a single system, we're going to have a list of models, somehow sorted by accuracy. So what do I mean? Let me see. Okay, let me just go there right away. Okay, and then I'll give you some example as well. Oh, sorry, let me switch. Yeah, somehow I couldn't really include this one here. I didn't have space, but just remember, failure is not an option. Right? Always remember when you build a system. Okay. Right, so it's something called correct by construction. This will be the formal method approach we're going to take for this course. Okay, let me explain what that really means intuitively. For the same system, you're going to have initial model M0. The subscript over here tells you which model it is, like an array of models. So, very simple question. How many models do we have in total? M models? M plus 1, right? That's something to make sure, right? I'm pretty sure you know, but I just want to make sure. M plus 1 models. Okay? N here can be 0, in which case it's only a single model for your system, right? It's possible, but not really recommended. So all the models over here, all models describe or formulates, describe the same system. The same. Okay? And let's talk about some special case. M0 is the initial. Oh, let me just do a little bit better. The initial, simplest, and most abstract model. Okay, just pause a little bit. I'll give you an example right away. Okay, what do I mean? The simplest and most abstract model. Let's see two examples that we're going to do in detail throughout the course. Let's say I want to build a bridge controller system. Let's say, okay? The simplest model I can have is like over here, like that. Oh, you know what? Before that, let me give you a little bit of context over here. The context is like this. You have a mainland. And also, you have some island. What you would like to build is a bridge between them. So this is a bridge. That's one way. So this is conceptually the system you actually want to build. But we don't necessarily have to build a very sophisticated model right away with sensors, traffic lights, and everything. We don't have to. The approach we want to advocate in this course is you start with something very simple, and you can already verify some very useful property already. So having this in mind, right, you got mainland, you got island, and you got bridge. Let's take a look at the initial model. It's very interesting here. Initial model here, do you see something is missing? The bridge is missing. That means as far as the simplest abstraction is concerned, we do not even have to consider the bridge itself. Instead, what we consider is we consider the island and the bridge as a simple compound together. And we'll consider mainland over here. That's it. But we'll see exactly how this initial model will work. For now, that's all I want to mention. So that's one example. Okay? Second example. The second case study we'll do will be some file transfer protocol. You want to transfer a file, maybe byte by byte, over the internet to another place, right? Maybe remote. And in that case, the simplest model you can have is something like this, okay? This one here. So this will be the sender side where we want to send a file with byte A, B, and C. And initially, nothing has been received. The simplest model talks about this. We abstract away, I'll write it down. We abstract away the time. We say that in order for you to transmit from this to this, it's got to be instantaneous. You will simply go from here directly to here without any lagging of the time. That's something we don't have to really consider for the initial model. We only add the notion of time and delay in the later subsequent so-called refinement. Okay? I'll just write down here, and we'll get to the file transfer protocol once we are done with the bridge controller. So abstract it away. Delayed in sending. In that way, it's only instantaneous. Okay? That's about initial model. We have seen two examples already. And that's about M0. What about MN, the last model? The last model there should be the opposite, right? Let's write it down. Oh, let me just make sure we are still fine. So this one here is going to be the final, most sophisticated, as opposed to simple, and most concrete model. All right? Let's see example right away, and I'll make it general, make a conclusion. In the bridge controller case, the most sophisticated model we're going to consider will be as follows, right? Over here. Number one, you can see now we do have a bridge. And then we have the notion about island and also mainland. And also we have the notion about how many cars are passing through. Also, how many cars are passing through this way. And also how many cars are actually in the island. And also, there will be two traffic lights. For example, if this traffic light happens to be red, that means the car from here cannot really enter into the bridge, and etc. So these are the details you don't really see in the initial model. Okay? That's the main point I want you to see. And what about a file transfer protocol? Remember the initial model we just saw? The transfer itself is instantaneous. Just simply go from here, empty, and you got it right away. Now, how can we make some refinements? We want to add in a little bit more information about how the transfer can be done. In that case, in this refinement over here, very quickly, we're going to transfer byte by byte by using certain maybe pointer over here. It's telling us which byte should be transferred. So now R is pointing to A, so A should be transferred. And then R is pointing to B, so B should be transferred, and etc. Right? That's more like more details added to the model. Definitely more sophisticated than the initial model. Hopefully you can really see, even without knowing the details, this diagram over here summarizes the following. You may have more than one models in your system. The first one should be simplest for you to analyze certain aspect. You can gradually add more and more details until the final one. And the final one should be close enough to working code that you can turn into maybe C or maybe some code or maybe embedded system code. Okay, the final one over here should be the closest for translating into code. All right, and I'll make sure I fit. Yeah, we've got 10 minutes. Okay, and the notion about abstract and also concrete, you can see abstract over here, and also concrete. So these are relative terms, which means whenever you're given two models, You want to talk about which one is more abstract and which one is more concrete. The only time you can make it more absolute is this initial model here and the final model here. Okay, let's talk about MI and MJ. These two in the middle, right? So these two over here, you can see here, MI, this one over here, is more abstract than MJ. That makes sense, right? Symmetrically, you can write it down. MJ is more concrete than MI because there is an order of sorting the model. Just have this kind of conceptual idea in mind, all right? And why are we doing this? Isn't it nice? Simply go directly to this final model directly. You might be thinking, I agree with you. That's what I thought when I was a student, right? So the idea would be, for any realistic system that's big enough, if you just want to prove all the properties directly on this final model, it's too large for you to prove. It's infeasible to do so. The idea would be, you try to distribute different properties into different models in the pipeline over here, so that you prove some property in the initial model. Once it's proved, it's there. And then you try to prove some other property here. Once it's proved, it's accumulated, and etc. That's kind of the idea. Already done over here. So number one, having a single model and proving all, so single and all, properties on it is infeasible, too complicated. Okay? And number two, I'll try to write it here. So the approach we're going to take will be, instead, distributes different properties to different models. Number two, for example, overall, let's say you want to prove 10 properties for your model. You may prove only one here, and then prove 2 here, and etc. Number three is also very important. The final thing you want to also prove is these models are not really unrelated. Formally, you want to say MJ, which is more concrete, is a formal refinement of MI. And we have to learn about how to formulate a proof obligation for proving MJ is a refinement of MI. We're going to do that, okay? So number three, let me write it down. Number three, we also need to prove MJ is a formal refinement of MI. Okay, sorry about the text being a little bit small here, but you will see that once I release the note to you. Guys, are we okay conceptually? Also, you saw some example, okay? So in here, a little bit look ahead. When we talk about the example here for bridge controller, we'll talk about this model first as an initial one. Nothing it refines because it's already the most abstract. When we talk about M1, we're going to prove some property about it. At the same time, we want to prove that M1 is a valid refinement of M0. And when we get to the final model M2 over here, we're going to prove some property here, and then we're going to prove that M2 refines M1. By the way, you don't prove that M2 is a refinement of M0 because it's transitive. If M1 is a refinement of M0, M2 is a refinement of M1, then by transitivity, M2 should be a refinement of M0. You don't need to prove it again, right? Everything hopefully is still straightforward, but once we get down to the math and dirty details, it could be a little bit tricky. That's something we'll definitely do, but keep that in mind. I think, let me see. I think I basically mentioned everything here. Please take a look at this, the slides. Okay, for one more slide and then we're done. We'll start you fresh on the math review next week, okay? So for this course, we're going to study example models of example models. and especially and also their proofs. The two system we're going to do will be bridge controller, which is a reactive system, and also we got also another one called distributed system, which is the FTP, file transfer protocol. And unfortunately, we wouldn't be able to discuss more examples because I'd rather go very thoroughly about how you can do these two. So if you're really interested, the draft textbook, or even if you're interested in purchasing the textbook, you will be able to see more, like a sequential and concurrent progress. That one will be completely optional. If you want to find more examples for yourself, feel free. And the Rodin platform will be the tool we're going to use to do some proofs and also specification. Okay? And for the Rodin, you're going to learn about properties, refinements, and also we're going to review classic logic and set theory. Right? Remember, partial function versus total function. Injective function, surjective function, bijection. Does it kind of ring the bell? If no, we're going to review. All right? I'll let you know. Well, I'll let you go earlier. Okay? Guys, thank you so much. Have a good weekend, and I'll see you next time. No, you don't need to go lab session today. No lab this week. Starting from next week.